Hi everyone, my name is Sanjana and I'm a third semester student studying in SVC Bangalore. In today's video, I'm going to be explaining a topic from operating systems. The topic for today's discussion is deadlocks. So first, let's take a look at what is a deadlock. A process requests resources, and if the resources are not available at that time, then the process enters a waiting state. Sometimes a waiting process is never again able to change its state because the resources it has requested are held by other waiting processes, and this situation is called a deadlock. So now let's see what are the necessary conditions for a deadlock to take place. A deadlock situation can arise if the following four conditions hold simultaneously in a system. The first one is mutual exclusion. At least one of the resource must be held in a non-shareable mode, that is, only one process at a time can use the resource. If another process requests that resource, then the requesting process must be delayed until the resource has been released. The second one is hold and wait. The process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. The third one is no preemption. Resources cannot be preempted, that is, a resource can be released only voluntarily by a process holding it after that a process has completed its task. The last one is circular wait. A set of waiting processes must exist such that the process, for example, P0 is waiting for a resource held by P1, and P1 is waiting for a resource held by P2, and so on. And it continues in like a circle pattern. Next, we have different methods for deadlock prevention. The first one is mutual exclusion. The mutual exclusion condition must hold for non-shareable resources. Shareable resources do not require mutually exclusive access and thus cannot be involved in a deadlock. Example, read-only files are examples of a shareable resource. If several processes attempt to open a read-only file at the same time, they can be granted simultaneous access to the file. A process never needs to wait for a shareable resource. Deadlocks cannot prevent by denying mutual exclusion condition because some resources are intrinsically non-shareable. Next, we have hold and wait. To ensure that the hold and wait condition never occurs in a system, then we have to guarantee that whenever a process requests a resource, it does not hold any other resources. One protocol that can be used requires each process to request and be allocated all its resources before it begins execution. Another protocol allows the process to request resources only when it has none. A process may request some resources and use them, and before it can request additional resources, it must release all the resources that it is currently allocated. The third one is no preemption. The third necessary condition for deadlocks is that there must be no preemption of resources that have already been allocated. To ensure that this condition does not hold, the following protocols can be used. If a process is holding some resources and requests another resource that cannot be immediately allocated to it, then all the resources and the processes is currently holding are preempted. The preempted resources are added to the list of resources for which the process is waiting, and the process restarts only when it can regain its old resources as well as the new ones that it is requesting. The last method is circular wait. One way to ensure that this condition never holds is to impose a total ordering of all the resource types and to require that each process requests resources in an increasing order of enumeration. Next, we have deadlock avoidance. To avoid deadlocks, an additional information is required about how resources are to be requested. With the knowledge of the complete sequence of requests and releases of each process, the system can decide for each request whether or not the process should wait in order to avoid a possible future deadlock. Each request requires that in making this decision, the system considers the resources currently available and the resources currently allocated to each process and the future requests and releases of each process. The various algorithms that use this approach differ in the amount and type of information required. The simplest model requires that each process declares the maximum number of resources of each type that it may need. And given this prior information, it is possible to construct an algorithm that ensures that a system will never enter a deadlocked state. Such an algorithm defines the deadlock avoidance approach. So in this we have two categories called safe state and safe sequence. A state is safe if the system can allocate resources to each process in some order until and still avoid a deadlock. A system is in a safe state only if there exists a safe sequence. Safe sequence. A sequence of processes is a safe sequence for the current allocation state if for each resource the request can still be satisfied by the currently available resources. And finally, we have different methods of deadlock recovery. A system recovers from the deadlock automatically. There are two options for breaking a deadlock. One is to simply abort one or more processes to break down the circular wait, and the other is to preempt some of the resources from one or more of the deadlock processes. So the first method is process termination. To eliminate deadlocks by aborting a process, we use one of the two methods within the process termination. In both methods, the system reclaims all the resources allocated to the terminated processes. The first one is to abort all the deadlock processes. In this method will clearly break the deadlock cycle, but at a great expense. The deadlock processes may have computed for a long time, and the results of these partial computations must be discarded and probably will have to be recomputed later. The second one is to abort one process at a time until the deadlock cycle is eliminated. This method incurs considerable overhead since after each process is aborted, a deadlock detection algorithm must be invoked to determine whether any process is is allocated any resources or not. The next method in deadlock recovery is resource preemption. To eliminate deadlocks using resource preemption, we successively preempt some of the resources from processes and give these resources to other processes until the deadlock cycle is broken. If preemption is required to deal with the deadlocks, then three issues need to be addressed. First one is selecting a victim, which basically considers which processes to be terminated and which ones to be preempted and given the resources to. The next one is rollback. So, like, if we preempt a resource from a process, what should be done with that process? Like, clearly, it cannot continue with its normal execution as it is missing some of the needed resources. We must roll back to the process to some safe state and restart it from that state. The last one is starvation. It is how to guarantee, the resources will not always be preempted from the same process. So that's it for this video. I hope the topic is clear. And if you found this useful, please drop a like and share it with your friends. Thank you.